Today is 1st October. So we are doing this session for week 10 today instead of day before yesterday. So in this session, first we will discuss two problems, the imbalance problem and the three coloring problem. And then we will go to the practice questions of week 10. And the week 10 assignment deadline is, I think, on Wednesday, if I'm not wrong. So let's begin. So today's So we are going to look at the imbalance problem and how the imbalance problem is FPT with respect to the vertex cover size. With respect to vertex cover size and how the integer linear programming optimization question is going to help us prove that the imbalance problem when parameterized by the vertex cover size is fixed parameter tractable. So this is the goal of this section of today's session. So let me first define the imbalance problem. Or are you already aware of about the definition of imbalance problem?
So it is better if you give a brief overview of the problem.
Okay, so just give the definition so that both of us, I mean, all of us are on the same page. So given a graph, so let us say the input is an undirected graph. The input is an undirected graph G. It has n vertices. So we define an ordering of these vertices. So an ordering of these vertices is a bijective function pi. So basically you are giving labels, numbers to these vertices from 1 to n. Okay. So this bijective function pi is an ordering of these vertices. So there could be n factorial different orderings of n vertices. So what we'll define, so we'll introduce two terms, L of v with respect to pi. So given an ordering pi, L of v, so v is a vertex. So for v, a vertex in the graph, for v, which is a vertex in the graph, we'll define L of pi, L of v with respect to v as the set of neighbors of v. So those neighbors of v that have received a smaller number by the bijective function. Okay, so we'll take an example. And similarly, R pi of v is those neighbors, is a set of those neighbors of v that have received a larger number than the label of v. Okay. And the imbalance at the vertex v, so let us, the imbalance of vertex v with respect to pi is the difference of L pi of v and R pi of v. But this number should be positive, so we are taking mod. So we're taking absolute value. So this is the imbalance at a vertex. Now imbalance of the ordering. So imbalance of this ordering pi so which is written as I of pi, is the sum of all the imbalances over all the vertices. Okay. So now let's take an example. So let us say this is a graph. Let's take a very simple graph. So it's a path graph in 3 vertices. So you first thing is you have to define an ordering. So let us say we define the ordering as, so we give this vertex label 1, this is label 2, this is label 3. So this is an ordering. So let us find out what is the imbalance at each vertex for this graph. Okay. So what is the imbalance? So let's just say, so ordering pi is so pi is like first vertex has got so what we can say, maybe we can call it ABC. So let's name the vertices. Then we cannot define the ordering. So this is A, this is B, this is C. So you are assigning numbers 1 to 3 to A, B, and C. So ordering is this: pi of A is 1, pi of B is 2, and pi of C is 3. So this is the bijective function. So what is the imbalance of 1? Uh, I should say what is the imbalance of A with respect to pi. So we have to identify that what are the neighbors of I that have received a higher labeling than A. So we want to compute R of A with respect to pi and L of A with respect to pi.
So this value would be equals to 1 here. And moreover, is this necessary that we only need to consider the neighbors of, I mean,
Yes, yes.
only the neighboring vertices?
That is the definition, that
Okay.
we have defined L of V with respect to pi as those neighboring vertices of V that have received strictly less labeling than the labeling of V.
Right.
So A doesn't have a neighbor which has received a smaller number, a smaller labeling than the label of A, because the label of itself is the smallest label. So L pi of A, so L pi with respect to A is going to be empty set. But R pi with respect to A is this set. I mean B. Right. So 1 minus 0 is the imbalance at A. Okay. So similarly, what is the imbalance at B?
So imbalance at B would be equals to 0,
Right. Why is that?
because the value of L pi of B is equal to 1 and the value of R pi B would also be equals to 1.
Correct.
So this is balanced here.
Right. So therefore, the number of vertices which are neighbors to B receiving a strictly less label than B is equal to the number of vertices in the neighborhood of B receiving strictly greater label than B, than that of B. So
Yes. And I was just thinking that even though this could be the imbalance problem, but is there any other problem in which instead of taking the count of the vertices, we do take their values? I mean the actual values. Uh, so
the
like here,
sets,
yeah. So because this is basically a permutation, so instead of taking that how many vertices differ in the neighborhood, uh, so we count that to what value the neighborhood is creating a difference. So like in this case, instead of 0, if we take the actual value, so then this could have been say 3 minus 1, and the value could have been say 2. So it could have created a difference of 2.
So you were saying that y only confined to the neighborhood of a vertex. That's what you were
No,
saying?
no, my question is not related to the only, I mean, considering only the neighborhood. So I mean to say that why are we only considering the vertices in the neighborhood and not their actual values? So like see here, say the value, because we have defined the VG as a bijective function. So therefore the value of this C is 3 and the value of A is 1.
Oh, you
So
mean the
there,
labels?
yes, labels. So is there, I mean, is there any other problem formulation in which instead of taking the vertices, we do take their labels?
Okay.
Because, yeah,
So you are saying that why not formulate the imbalance in terms of
yes,
the difference in the labels and
yes.
so
Because this is a bijective function, so every value will get mapped to a distinct value. And yeah, I was just
so
thinking that okay, there could be some other problem which could be, I mean, in which these labels would have been considered.
yes, it's a valid question. So maybe depending on so whoever has designed the question, they had some other problem in mind, and while solving that problem, maybe they thought that this is an abstract way of posing the problem. But depending on the application, what you said is a distinct possibility that maybe for some application we may need to consider the difference in the absolute labels instead of the count of the vertices. I mean, the imbalance should be counted as the difference in the labels of the vertices on two sides. So some of the vertices are strictly less, some of the vertices are strictly more, and then you can do a count or you can do a uh, subtraction between the labels also. But
Yes,
I have no insight into why this is defined the way it is.
yes. This is the definition of the imbalance problem. Yeah, right.
Yes. So that is how. So Shivang, are you on board? So we are doing this session because he has requested. Uh, yes. All right. So yeah. So far we have seen that the imbalance at A is 1, but the imbalance at B is 0. Uh, what is the imbalance at C? So as you see, the imbalance at A and the imbalance and C are supposed to be equal because they are nothing but identical vertices having only one neighbor. But we can do it formally. So C has only one neighbor, and that neighbor has received label 2, which is less than 3. So L of P with respect to pi is 1, but it doesn't have any other neighbor. So L of R of P with respect to pi is 0. So therefore the imbalance at C is 1. So therefore the sum of the imbalances across the vertices is the total imbalance of this ordering. So this is 1 plus 0 plus 1, that is 2. Okay. So but uh, okay, so what is our objective? Our objective is to minimize. So our objective is to find an ordering of these vertices. So we want to label the vertices from 1 to n given an n vertex graph such that the total imbalance of the labeling of that ordering is minimized. Okay. So do you immediately see that two different orderings, two different bijective functions labeling the vertices may lead to two different imbalances?
Uh,
Is it immediately
yes.
obvious or it requires some explanation?
So yeah. So this is obvious because if we start labeling these vertices, say in the order say 2, 1, and then 3, so then we will get different imbalance.
Okay.
2, 1, and then 3. So now the value of the I pi of A is equal to, so the value of L becomes equals to 1, and the value of R becomes equals to 0. So then this difference comes out to be 1. It's same. But if I could have done this in a different way, no. So if I yes, but now in this case, it's not clearly
Okay. So
yeah.
it's not immediately obvious that maybe any random permutation, any random labeling of the vertices are going to lead to the same imbalance. So we're not immediately sure. But let us compute. Let us see that okay. So I pi of A turns out to be 1 even in this labeling. So what about I pi of C? So
So I pi of C here is equal to the value of left becomes 0, and then the value of right becomes the value of right stands for greater than, and the value of so R pi right is 0 and the left is equal to 1.
okay.
So I pi C is equal to 1. Yeah. So in this case, the results are same actually with the different assignments, with the different permutation, the results are same. But if we could, if so, had there been more vertices attached to B, then probably we would like to assign lesser values to those.
No, but
Uh,
what? Let us see what is the I pi of B.
so I pi of B is that the value of L is those who are smaller than 1 is 0, and those who are larger than is 2, but then the value remains the same. That is true.
Why is it same?
No, no, it is not same. Yeah, earlier it was 0. Yes, yes, you're right.
Yes. So it is
Yes,
4 now. So the imbalance, total imbalance, the imbalance of the ordering is now 4.
yes, yes, yes.
So it turns out that two different labelings may lead to different imbalances. So our objective is to find that labeling such that the imbalance is minimized. Now there are how many labelings for an n vertex graph?
So there could be factorial of n number of the possible labelings.
Correct. So for the n vertex, so if there are so you have n numbers to be assigned to these n vertices. For the first vertex, you have n choices. For the next vertex, you have n minus 1 remaining choices, and like that. And it turns out to be total number of choices is n factorial. So there are n factorial uh, number of choices. So that is already a very large number, exponential number. So what we will show is that there is an algorithm. So our ultimate aim is to show that one can find. So this is the final. So this is our goal. So final theorem that, or rather, I should not write theorem. Theorem is. So I'm writing from the book. So our goal is to provide an algorithm that runs in that finds the optimal labeling or the ordering of the vertices in time 2 to the order k into the order 1, where k is the size of a given vertex cover in G. So along with the input, so what is the parameter? The parameter is k. So along with the input graph G, you are given a vertex cover of G, and the vertex cover of G has size k. And for our purposes, if G is a constant, then this number, although it looks quite large, it is going to be a constant. So this is going to be a polynomial time algorithm. So this is the whole objective of the uh, imbalance solution that we are going to discuss.
So what this expression here is 2 raised to the power of the order of k multiplied by n raised to the power of the order of 1, or what?
Yes. So this is 2 to the order k into
Okay, yeah.
Polynomial in n.
Yes, yes.
So this is the whole objective. So I think right as Shivang rightly pointed out, the analysis is slightly involved. So we will do it step by step, and hopefully we'll be able to understand the analysis. Okay, so we have seen integer linear programming formulations of several problems, including the vertex cover problem. So what we are going to do is that for this problem, for the imbalance problem, we are going to formulate an integer linear program. And if we can formulate an integer linear program, so there is a theorem which says that the integer linear program instance of size L with p variables is fixed parameter tractable. So this implies that if we can convert this imbalance problem, or if we can write an equivalent ILP formulation, integer linear program formulation of the imbalance problem, then because ILP is fixed parameter tractable, in the number of variables to write the ILP, and if we can write the ILP formulation of the imbalance problem such that the number of variables is 2 to the order k, then we will be able to solve the imbalance problem in this much time. Is that understood? So that is the blueprint of how we are going to prove this theorem, or how we are going to achieve our goal.
Yes.
Okay. So now let's focus on how we are going to write this integer linear programming formulation. All right, Shiva. Okay. So what is our input? So our input is not only a graph, an unrated graph. Along with that, we have a vertex cover. Okay, so let us say that we have a vertex cover X that is part of the input. So X is a vertex cover of G. And let us say that the number of vertices in X is K. So we have a K-sized vertex cover given to us. All right. So let us say that the vertex cover given to us is comprising of these vertices. Right. So in the optimal ordering of the vertices that minimizes the imbalance, there is an ordering of these vertices also that are part of the vertex cover. So the optimal ordering of the vertices of the whole graph imposes a fixed ordering of the vertices of this vertex cover. Okay. So let us say that ordering, so let pi be the optimal ordering that minimizes the imbalance. Okay. So there exists an ordering. So pi imposes an ordering on the vertices of the vertex cover which is given to us, and let us say this is the ordering. Okay. So in that optimal ordering, U1, the vertex U1 has received the smallest level, U2 has received the next smallest level, like that. UK has received the largest level. So we will try. So since there are k vertices in the vertex cover, so there are k factorial possible orderings of the labels of the vertices in X. Okay. But k factorial is a constant for our purposes. K is a constant, so we can afford to try all these k factorial possible orderings and try to see if from that ordering. So we do not know this ordering. This ordering is not known to us. We will try all possible k factorial orderings and we will try to see that from there, can we obtain the entire ordering of the vertices? Okay. Okay. So now consider the vertex set. So all the vertices which are outside of X. So let I be equal to the vertices of X minus X. So this is all the vertices which are outside of X. Okay. So let us just draw this. So let us say this is the set of vertices in X and the other vertices, all the vertices which are outside of X. Okay. In the graph, this is I. Bg minus X, and we say that okay, this is equal to I. So what can we say about I?
So then there would be factorial of n minus k number of the possibilities left.
For
No.
labeling the rest of the vertices.
Yes.
That is not the question. So my question is, do you see any structural property of the vertices which are not in X?
So since k number of the vertices are the part of the vertex cover, so they are covering all the edges of the given graph.
Yes,
And for the remaining vertices, I mean, so remaining vertices may be thought of as the redundant vertices, which are not required as far as the coverage of all the edges is concerned.
exactly. That is right. So there is a so Shivang is writing something. Let us wait for him. You can as well feel free to unmute yourself and say what you wanted to say. Any thoughts, Shivang? Okay, so he doesn't know. Fine. So he says no. So these are the vertices which are outside of X, and they are not participating in the vertex cover. They're not the vertex cover vertices. So that means that an edge joining any two vertices, if at all such an edge exists, that will be a violation to the fact that X is a vertex cover, isn't it? If an edge between two vertices lying in I exists, then how can X be a vertex cover? If X is a vertex cover, then for every edge, at least one of the endpoints should have been in X, isn't it?
Yes.
So therefore, such an edge between two vertices, any two vertices of I cannot exist. So all the vertices here are such that the edges out of these vertices are going to X only. There are no internal edges, right?
Yes.
So
Yes.
in other words, these vertices can be thought of as an independent set. Okay. So an independent set is a set of vertices such that no two vertices has an edge between them.
Yes, but then there could be edges from inward being, say, one endpoint in I and the other point in X. So this could
Yes,
be a
yes,
possibility.
yes, yes. So that is not preventing I to become an independent set.
Yes.
So this is okay. So what we just claimed or showed that this vertex which is outside of X is an independent set, isn't it?
Yes.
Right. So now we can proceed. Let's now define. We're just going by step, otherwise it is going to be difficult. So let us define what is called type of a vertex in I. So for a vertex, so I is the set of vertices. So I is the independent set. So let us have a definition. So the type of a vertex, okay. So V is in I. So let us do it this way. So for all vertices in I in the independent set, type of a vertex V is the neighborhood of V. So I'll write it this way. So is the set of vertices that are in the neighborhood of V as well as, I mean, I think this much is sufficient. Yeah, this is sufficient. Correct. So what this means that type of, so what is, so consider a vertex. So this vertex is connected to, let us say, multiple vertices in X. So X has so many vertices. So out of that, the set of vertices are neighbors to X, to V. Let us say this is V. This is V. So we're taken one vertex, any vertex from I. So now it has some neighbors in X. So these set of vertices in X, which are neighbors to V, that is called the type of V. So basically, it's a subset of X. Okay, so type of V is supposed to be a subset of X. Maybe all the vertices in X are in the neighborhood of V, but this is the definition. So you understand what is the type of a vertex.
Yes. And now here we are not talking about the type of an individual vertex of the set I. Rather, we are defining this type V for all the vertices of the set I, and whatever we get would definitely be a subset of the set X.
For every individual vertex, we have defined its type. So maybe there is one more vertex that has the same neighbors as the vertex of V, then that has the same type. Okay. So it is
Okay.
possible, very much possible, that V1 and V2 are two vertices that has the same neighborhood, identical neighborhood, connected to the same set of vertices in X. That is very much possible. Then we'll say that type of V1 is equal to the type of V2.
Okay. Yeah.
So the type is with respect to a vertex in the independent set. Okay. So how many possible types are there?
So whatever the type is, it will definitely be the subset of the set X, and at the most, the union of the type of all the vertices in the set I would be equals to the set X.
That is also true. But my question is, how many distinct types are possible?
Okay, so okay, okay, distinct types. So one vertex can map to all the elements of the set X.
Just a second. The one vertex can map to all the elements. That is true. How many distinct types are possible? That is the question. So, so any subset of X is a possible type, isn't it?
Yes, yes.
So the number of possible types is nothing but the number of possible subsets of X, isn't it?
Right, right. 2 raised to the power k.
Yes, exactly. Is that right? Shivang? It would be mod X. It won't be mod X. So we are just, you know, why it is 2 to the k or 2 to the x? Because we do not know, we do not have any control about what is the neighborhood of a vertex in I. So the neighborhood of a vertex in I could be any subset of X. We do not know. Right. So now, right. Now you're okay. So you're on board with the fact that 2 to the mod X. So K is mod X. So the number of distinct types is 2 to the mod X. Okay. Okay, so now we are in business. Okay, now what we are going to do? So if two vertices have the same type, so that means if they are adjacent to the same set of vertices in X, then we are going to club them together. Okay. So for a type S, for a type S, S is a subset of X. So we define I of S as the set of all vertices in I of type S. Okay. So all those vertices which have the type S are clubbed together and we call it I of S. All right.
Yeah, so it's a kind of codomain of the S kind of thing,
Yes,
isn't
it's kind of saying the reverse thing. It's
it?
sort of,
Yes.
yes. So it is mapping and this reverse mapping. Okay. So you're taking the inverse in a sense. Okay.
Yes.
So why we are doing this? Because we know that how many, so we have a handle on how many distinct types are there. That we know it's only 2 to the power k, and for our purposes 2 to the power k is a constant because k is a constant. Okay. So if we define this, so we know there are we can only define 2 to the power k different such sets. Okay. So in a way, it is the fingerprint concept that we had before. That these vertices have the same fingerprint. Those vertices have the same fingerprint are kind of clubbed together. All right. Fine. So now we are in business. So let's draw a figure. So what we are doing basically, so we have clubbed the vertices in S in I into pieces. Okay. So we have been able to club the vertices in I into pieces. And we are saying that okay, this piece is corresponding to some S. So all the vertices in this piece have the same set of neighbors in I. We have been able to do this clubbing of the vertices in I. All right. Okay. So now, so this set has a different set of vertices, right? This set has a different set of vertices. This set has a different set of vertices in X. So like that. Now we are going to formulate the ILP. With all this notation in hand, we are going to define the variables and constraints of the integer linear program. And that will be, our intended goal. Okay. So let us define the variables. So let X super I sub S be the variable that encodes the number of vertices of type S. Oh, I have to define location also, right? Okay, one more thing we have to do. So let me define location. Okay, so we have defined the notation and now we will define something called location. Okay. So notice that we have decided, an ordering of the vertices of the vertex cover. Okay. So there are k factorial possible ordering. So we have decided one order that, okay, we are going to label this vertex as this. So we have this ordering of the vertices in the vertex cover, not all the vertices. Okay. So now we have, so there are n vertices. So out of the n vertices, you have fixed that, okay, I am going to put the k vertices in this order only. So these are k vertices. All right. So these are the vertices in the vertex cover. You have decided their labeling. Okay. So, but we have not decided that how many vertices are going to be in between. So how many vertices in the graph are going to get label between the label of the first vertex and the second vertex of our vertex cover? That we have not decided. Okay.
This point is not clear. What is not decided?
So see, uh, what is our goal? Our goal is to find that labeling of the vertices that minimizes the imbalance, the overall imbalance. Okay.
Right. So even while assigning these values to the vertices within the vertex cover, I should have taken the help of some other parameter, like say the degree of the vertex into the consideration, and clearly say if the vertex 3 is having the lesser degrees, is having the highest degree, so then I should assign such a number to that vertex which contribute the least to the total imbalance thing. So because the different labelings will contribute to different things to the imbalance, and here within the vertex cover also we should go for the optimal labeling of the vertices.
What is it? So you are suggesting some greedy criteria. So what is the greedy criteria?
So greedy would be the one that the vertex which has got the highest degree should be assigned should be assigned the so like and the one which is having the highest degree should assign the number one as a label, and all the neighboring of that vertex which has got the highest degree as the values like say 2, 3, 4, 5. So
So what if
that
what if the graph is a uniform graph? All the vertices have same degree.
So yeah, in that case, it will not matter. So right now, what is happening here? That on what basis, or this is an assumption, on what basis we call this pi as an optimal ordering? Uh,
So we are not going to. So we have not found pi. We are going to find pi, and the integer linear programming formulation is going to give us a pi.
okay,
We
I
have
see.
not found pi yet. We have just decided an ordering for the k vertices. In
Uh-huh.
fact, there are k factorial vertices, and so we will solve k factorial subproblems. We will have all this for all these k factorial fixed orderings of the k vertices in the vertex cover. We will solve a problem, and whichever gives the best, we will take that. Something like that. You understand?
Okay, okay. Yeah, yeah. Now I understood. Yeah, clear, clear.
Yes, because we have the currency, so we are rich enough to spend k factorial time because k factorial is only a constant.
Yes, yes.
Oh, I understand your doubt now. So you're saying that why are you taking only one fixed ordering of these vertices? We are taking all the orderings.
Yes, yes. Now it's clear.
Okay, so now so we are going to solve k factorial problems, but one of the problems. So we are looking at the run of one of the iterations. So in this iteration, we have decided that okay, this is going to be our ordering of the k vertices in the vertex cover. But we have not decided what are the number of vertices in between. So this vertex has labeled some label. So this is the smallest label. So there are n levels we have. So how many labels are in between the label of the first vertex and the second vertex in our ordering? So you understand what I'm saying? So this number is not known to us. Let us take an example. Uh, so let us say there are some vertices. I'm just making up. Let us say A, B, C, D are four vertices, which are in the independent set, which are not in the vertex cover, and we have not decided their labeling yet. What have we decided is the labeling of the vertices in X in the vertex cover, but not in I. So consider the four vertices in I. So we do not know whether the labeling of whether the labeling of A is lying between labeling of 1 and 2, or it is lying between labeling of 2 and 3. We do not know. Okay. But the labeling could be anywhere. So there are, so to say, K plus 1 pockets. So labeling could be strictly smaller than the label of 1. That is one pocket. So if A lies here, we'll say, oh, it is in pocket 1. The labeling of A is in pocket 1. So this is pocket 2. Pocket 2 is between the labeling of 1 and labeling of 2. This is pocket 3. Like that. How many pockets? This is kth pocket. This is K plus 1th pocket, isn't it?
Yeah. So we have k plus one number of the pockets here, and so it's true then. So if we consider these as the say k plus one number of the boxes and to be filled with how many number of the objects? The n number of the objects?
No, n minus k. K is already decided, right?
K is decided, yeah. So yeah, it's all right. Yeah.
Yeah, so there are K plus 1 pockets, and we do
Mhm.
not know which vertex has gone to which pocket. That we'll have to find out. That is the task, isn't it?
Yes, yes.
So now we are in a position to define the variables of the integer linear program. So for every I between 1 and k, so I is, sorry, between 1 and k plus 1. So these are the pockets. And every s. So what is s? So s is, as we defined before, uh, so s is some type. So how many possible types? 2 to the k possible types. So S is some subset of X. Oh, sorry, X is there. So S is some subset of X. For every subset of X, for every subset of X and every I between 1 to k plus 1, we are going to define a variable X sub S I. So take a moment to sing that in, that we have. This is a pretty involved integer linear program formulation, and I I agree with Shivang that there can definitely be doubts on this. So yeah, so X sub Si is a variable that we are going to define for every S, which is a subset of X, the vertex cover. So how many subset of X, distinct subset of X are possible? Only 2 to the K. And for every I is corresponding to these pockets. So let me define what does this variable encode. So this is encoding the number of vertices of type S that are in pocket I.
Yes.
So what are the types? So let's recapitulate. So we have defined the types. So for every vertex in the independent set, we have defined its type. So all these vertices have types, these vertices in the independent set. So now the type is nothing but a subset of X. Now there could be multiple vertices of same type, and those we have clubbed together in bags. So those bags we say I of S. And then we know the number of such bags is also bounded by 2 to the K. Okay. So the number of vertices of type S that are in pocket I is denoted by X by S. So let's draw one more picture. It is slightly complicated. So this is X. This is a vertex given to us. And let us draw these bags. So these bags together, this is the set of independent sets. So all the vertices in one bag have the same S. So they are adjacent to the same set of vertices in X. Okay, so let us say this is S1. Let us say this is S2. Okay. So now I am saying that, okay, Now that you have I of S, so I of S is a set of vertices that have the same signature S, that have the same set of neighbors S. Okay. So how many of these vertices have you put in this pocket? How many of these vertices have you put in this pocket? So for each of, so to answer that question, that how many vertices of type S are in this pocket, we have a variable x sub si. Yeah. Are you with me?
Yes, yes.
Now take a moment. So now if you are with me, then you have to tell me that how many variables are there? How many x sub si variables have to be defined at most?
So what is the size of the gap in between two stars? How many elements can be accommodated here in between say 2 and 3?
That is some variable. Let's call it 2, 3, x23. So the number of, so the sum of these gaps, the number of variables in pocket 1 plus number of variables in pocket 2. So the sum of these variables in all these pockets should sum up to n minus k.
Uh, okay. So since I have n minus k number of the slots available here, so n
No, no,
minus k
number of
number
slots is only k plus 1.
k plus v. So n minus k number of the objects are to be distributed into the k plus 1 number of the boxes. So this will come out to be n minus k n minus r plus 1 cr. So that value comes out to be,
What did you just say? This we'll write it down.
yeah. So in how many different ways can I distribute n number of the objects into r number of the boxes, uh, wherein any box, I mean, wherein any
You
box
are
can be
answering a different
accommodated.
question. So you are answering the combinatorial question of how many ways we can distribute objects. So that is not the question. How many ways some objects can be distributed into some bags? That is the question you are answering. So my question is different. My question is, if you have defined x sub si in this way, such that for every s is a subset of x, and for every pocket I between I and k plus 1, you have a variable that encodes the number of vertices of type s that are in pocket I, then how many variables you have to define? So how many such variables do you define? I'm not
Okay,
asking
okay,
you that in how many ways you can do this, distribution. I'm just asking
uh,
you how many such variables we need to define.
okay, okay. So yeah, so so I need to define variables like say, so I can vary from 1 to k plus 1, and then s can vary from
Yes.
s1 say till sk, such that the union of s1 union s2, such that this union comes out to be equals to k. The cardinality of this entire thing comes out to be k. So
You are partially right. So for
yeah,
I, there are k plus 1 choices. And for S, which we answered, that how many distinct types of S are possible.
2 raised to
Okay.
the power k. Yes,
So therefore, the number of variables is nothing but 2 to the k into k plus 1 at most. That
yes,
is the
yes,
number of variables. Okay.
yes.
So the number of variables, now we're already in business. So the number of variables. So we said that if we formulate the imbalance ILP, and if that imbalance ILP, integer linear program, has only this many variables, then the running time of solving the ILP is going to be 2 to the power 2 to the power k into k plus 1, which we want. So as long as, so 2 to the power 2 to the power k is going to be a constant because k is a constant. So that was our initial goal. So we are in the right direction. So our goal was to find an optimal ordering of the vertices in time this. And I said that if you can formulate an ILP where the number of vertices is bounded by 2 to the some order k, then you can achieve this running time for solving that ILP. parametrically. So the number of vertices we have a bound. So we have only defined, we have to define some more vertices and then we will write the constraints. Okay, so it is about 7 o'clock. So let's do one thing. In the next 5 minutes or so, we are going to define all the vertices. And then either we can take a break or we can finish it off. And then we can take a break. Okay. Okay, so now so what we have defined so far, IS. So we have to remember that IS is a set of all vertices in I of type S. So these are the ISs. In fact, here we have IS. Okay, so now define one more variable. So for every vertex UI in the vertex cover is X, introduce a variable yi, so that represents a lower bound on the imbalance of UI. So we have seen how to compute the imbalances. So we define a variable UI, given yi, for a vertex UI in X. So that is going to be a lower bound on the imbalance of UI. What else do we need? So for every vertex UI in the vertex cover, we are going to define EI. So EI is the number of vertices in the neighborhood of EI that are lying to the left of I in the ordering of the vertices that we have already fixed in the vertex cover, minus the number of neighbors of UI to the right. So this is some more notation. So let me translate it for you, simple terms. Okay, so this thing I have to tell. So this ordering that we have fixed, so the ordering of the vertex in the vertex cover we have fixed. So the first I vertices in this ordering, we denote it by xi. So the first I vertices, that means out of the k vertices of the vertex cover, the I vertices that have received the smallest labeling, okay, the vertex that has received the smallest labeling, the second smallest vertex, like that, the ith smallest vertex, all these vertices together, we call it xi. Okay. So let us say that labeling wise, the ordering was this, that U1. So let us say all this UI belongs to X, and U1 has received the smallest labeling, U2 has received the second smallest, U3 has received the third smallest, and like that, there is an UI that has received the ith smallest, and so on, UK. So the first I vertices, we call it this set of first I vertices as Xi of the vertex cover X. So now,
But they need not to be neighbors among themselves. So like this is not necessary that U1 and U3 are neighbors.
no, we are not claiming anything about the neighborhood relationship among the vertices of the vertex cover. We are just saying that, okay, what is the first constraint we are going to write? So the first constraint we are going to write is, so we have to first see, we have defined these variables. We have defined these variables. We have defined the variable yi also. Now we want to say that there is some relationship that is going to define the constraints on the ILP that we are going to formulate. So how do you define the constraints? So you have to say that, okay, what is the imbalance of a vertex in my vertex cover? So let us say that we fix one vertex in the vertex cover ui. So we want to say that the vertex, we want to say that if yi is a lower bound on the imbalance of ui, that means if the imbalance of ui is at least yi, then there is some relationship we can find between this xis and yi. So that is our whole objective. We want to write an inequality that is going to the constraint. That is how the ILP will be formulated. Okay, not easy. It's quite complicated, I would say. So Shivang, are you with me? So I would encourage you to read from the book also, because uh, there are so many things involved. I'm not sure how much I'm able to transfer, how much knowledge I'm able to transfer to you. Uh, but it is inherently slightly complicated, the formulation of this ILP. Fine. So let me write the constraint. So the constraint is yi. That means the imbalance of ui, the imbalance of the vertex ui is at least pi plus. Okay, so I should probably make things slightly simpler. Before writing this, I'll write one more step. Okay. So let's try to translate what this means. So we have defined for every vertex in the vertex cover a variable called ei. So ei encapsulates the imbalance of the vertex ui with respect to the vertices in the vertex cover, but it does not encapsulate the imbalance of the vertex ui with respect to the other vertices, the vertices which are not in the vertex cover. Okay. So what is the first term? The first term is saying that look at all those vertices in the vertex cover which are to the left of ui. That means which have smaller level than the level of ui, and count them. So this is L of ui. No, this is not L of ui. This is L of ui is this thing plus the imbalance which is coming due to the vertices outside of X. So, but due to the vertices which are inside the vertex cover, what is the imbalance of ui? That is the reason we have taken X sub I minus 1. So this is L of the vertex ui with respect to pi, but only partially due to the vertices that are in the vertex cover X. So similarly, this term is the imbalance that is, so this is the right, this is corresponding to, we are counting the vertices which are to the right of ui in the vertex cover. That means having level more than that of ui. All right. So this is the imbalance coming to the vertex ui due to the vertices in the vertex cover. Okay. So we want to count what is the imbalance of ui. So that we have divided into two parts. One part is ei, which is the imbalance which is coming due to the vertices in the vertex cover. But the graph is not only the vertex cover. So ui is here. So ui has some neighbors in X, but it has some neighbors outside of X also, some neighbors which are in the independent set. So there is some terms which are to be written, which will contribute to the imbalance of ui from I. Okay. So let me write it down. It is also an expression which we need to uh, which we need to spell out in layman's terms. This is all in the book. If you go to the book, page number 138, then in chapter 6, integer linear programming, as miscellaneous chapter, integer linear programming section 6.2 section, 138 page, you will get to see. So let us see if we can take away anything from this expression. This is another complicated expression. So you have to recollect what are the meanings of these variables. Okay. Okay. So what I was saying is the following. So yi is the lower bound on the imbalance of a vertex ui in the vertex cover, and yi consists of two terms. One term is the imbalance which is contributed by the vertices in the vertex cover itself, which we have seen is this. But how about the imbalance which is contributed by the vertices which are in I? Okay. So now, so let's try to say we have taken a sum over all the subsets of X. So see, once we have fixed as S, so S is a subset of X. So once we have fixed S, and if Ui belongs to S, so let us say we fix an S here. This is S. So let us say UI is lying here. So UI is here. Let us say this is UI. Okay. So UI is a vertex in X. Also, it is in S. Then, so what does this variable mean? So this is, remember, the number of vertices which are, so the number of vertices which are of type S. That means those vertices out in I which are neighbors to all the vertices in S and are in pocket I. So we are taking the sum over those pockets which are strictly less than I. Okay. So UI is the ith vertex. Remember, UI is the ith vertex in the order that we have decided for the vertex cover. So in this ordering, UI is ith vertex. So all the vertices which are to the left of it that have received strictly less label than UI, we are taking the sum of all those vertices. So this is the sort of L pi of UI portion, and this one is the R pi of UI portion. Correct. Okay, so spend a moment. So I said this is not one, this is pi. Okay, so this is I. Right. So this is the sum of the imbalance. So this is the imbalance is coming from the left, and this is the imbalance coming from the right. We are going to take the, by definition of imbalance, the overall imbalance is the difference of them, and then we are taking the absolute value. So if you understand the definition of these variables, then if you stare at it long enough, then you will be able to understand that this term on the right hand side is nothing but the imbalance that is coming to ui, a vertex in X, due to the vertices in I. Okay, so yeah, so maybe I will give you some. Okay, so there is a message. Okay, so maybe I'll give you some time, and maybe at this point we can take a break, and you can stare at it, and you can also read the book. So page number 138, last equation, and then we can resume after 5 minutes.
Yeah. Okay.
Okay, let us start again. So I hope you had a chance to ponder over this inequality and why this inequality sort of encapsulates the imbalance at the vertex EY, which belongs to X. Okay. So this is going to be one of the constraints of the ILP. Okay. So these are the vertex variables. So we have encapsulated the relationship between these variables. So which have, but this is, remember, is not a linear constraint. So we have to remove the absolute symbols. So, so if somebody says that y is greater than equal to mod x, so equivalently we can write that y is greater than equal to x and y is greater than equal to minus x, right? So if you look at the book, that's what they have done. So there is one constraint which is yi greater than equal to this thing. The other constraint which is yi greater than equal to minus of this thing. Okay. So there is one more constraint. So what is is? Remember we defined is here. Yes, here. So is is a set of vertices in the independent set that have the same neighborhood S. So the number of vertices in is should be equal to the sum of the sets, sum of the cardinalities of the sets, where each set is uh, denoting the number of vertices of type S at different pockets. So there are k plus 1 pockets. So because there are k plus 1 pockets, so is is nothing but, so the cardinality of is, number of vertices in the independent set with neighborhood S, is nothing but the sum over I from 1, 0 to k, there are k plus 1 pockets, xis. So what is xis? It is a variable that encodes the number of vertices of type S that are in pocket I. So over all the pockets, the number of vertices of type S that should sum to the total number of vertices of type S. So that is another constraint. So this is one more constraint. So let's call it. So this is over all the subsets of X, and we know there are 2 to the k subsets. So there are 2 to the k constraints of this type. This is one more constraint which I said how it can be converted from non-linear to a linear version using this observation. Yeah, that's all. And we want all these variables to be non-negative. All right. So for all k lying between, so all I lying between 0 to k and all is subset of X. This you can look up from the book also. These are the constraints. So now we have to decide what is the objective function. The objective is to minimize imbalance. So to do that, we have to define one more, not a variable, constant. So remember, so we have a fixed ordering of the vertices in the vertex cover X. So we'll define ZIS to be equal to the imbalance at a vertex of type S if it is placed in pocket I. So remember we had defined these variables XIS corresponding to uh, the uh, the vertices in the vertex cover X. So this is also for the vertices of I. So ZIS is the imbalance at a vertex of type S. So type S means, okay, so ZIS is corresponding to the vertices. Remember the definition. So we have defined type for every vertex in the independent set. So for every vertex that is of type S, so in this box, we will define zeta S to the imbalance at a vertex of type S if it is placed in pocket I. So there are k pockets. So that means zeta S can also be computed exactly. So you consider all the vertices which are to the left of I and all the vertices to the right of I and take their difference. So that is the imbalance of a vertex of type S if it is placed in pocket I.
So what is the difference in between XSI and then ZSI?
So let us look at the definition. So XSI is the number of vertices of type S. That means those vertices which are in this box, I of S, that are in pocket I. So that means if you look at the ith pocket,
No, but then the S vertices, I mean S set is there in the set X and not in the set I.
yes, S set
It
is
says,
S is a
yeah,
subset of X. Correct.
yes. So it says that the number of the vertices of the type S,
Yes.
and type S is clearly the element of the subset of X that are in the pocket I. Yeah, because you draw the green circle in the set I, so I thought that no. Instead of here, I mean the this XSI would be having the vertices within the set X, isn't it?
Yes. Uh, so these vertices which are corresponding to type S. Okay. So out some of these vertices have gone to pocket I. Some of them has gone to pocket I plus one or one, two. So they have been distributed over this k plus one pockets. So
Yes.
so xi is defined with respect to the ith pocket and type S. So some subset of X. So S is a subset of X.
Yes. So then this, I mean, so can we have vertices of the set I as a member of the XSI?
Vertices of the set I. I is the entire set.
Yes.
Yes, of course.
Yeah. So we would only be having the vertices of the set I as the elements of the XSI, and this XSI stands for their count.
Correct. Exactly.
Yes. And now what happens in case of ZSI then?
That is that is defined with respect to imbalance.
Okay, imbalance of the type S if it is placed in the pocket I.
Yes. So
Okay.
all those vertices which are of type S that are in pocket I. So out of the vertices which are of type S, so look at this box. Some of them are in pocket I, not all of them. Maybe four of them are in pocket I. Now their imbalances is encapsulated by this variable.
Ah, yes, it's clear now. Yeah, fine.
Okay. So I'm sorry, this is quite complicated, uh, but
You have already made it so very simple for us to understand, but the proof itself is very complicated actually.
yes, there are so many summations, double summations to say these things in simple terms, layman terms. It is a challenging task.
Yes,
But
yes.
if you read it once, if you haven't read it, I am sure you are not getting full of it. If you read it once, I think you will get some idea what is going on. Uh,
Yes.
so we want to minimize imbalance. So now we know that we have yi, these variables are corresponding to the vertices in the vertex cover. So we defined yi. So where is yi definition? So we defined yi for every vertex in the vertex cover. We said it's a lower bound on the imbalance of ey, and then we computed partially what is. So this is the total imbalance for a vertex in the vertex cover. So total imbalance will be the sum of the imbalances. So this is the sum of the imbalances for the vertices in the vertex cover. Plus, there would be imbalances for the vertices which are in the independent set. So that is again a complicated looking double sum, but we will try to translate it into simple terms. Okay. So this is the reason we defined ZIS and XIS. So we want to compute that what is the imbalance contributed by the vertices in the independent set. So what are the imbalances of these vertices? So this is encapsulated by this term. So what it is doing is, so fix an I, so fix a pocket. So these vertices which are in the independent set has gone to some pocket or the other. There are k plus 1 pockets. So after the labeling, every vertex in the independent set has gone to some pocket. So fix a pocket. So let us say 0th pocket, that is the leftmost pocket. Okay. I is equal to 0. So now pick some subset of x. X is the vertex cover. So now for all those vertices whose neighborhood is S. So look at this diagram. So consider those vertices which are in IS. That means whose neighborhood is exactly S. And those vertices which have gone to pocket 0. So for all those vertices, we have a term ZIS into XIS, which encapsulate the imbalance of these vertices. Okay. So XIS is the number of such vertices that has gone to pocket I, and they are of type S. And the imbalance of such a vertex is fixed because the neighborhood is fixed. Because the neighborhood is fixed, S. Therefore, the imbalance is also fixed. Because imbalance is defined with respect to neighborhood. Right? So given a labeling, given an ordering, so imbalance of all those vertices which are in pocket I and of type S, their imbalance is fixed to be ZSI. So we take this term to mean the imbalance of these vertices which are of type S and going to pocket I. Okay, so now you are taking the sum over all pockets and all S's. So then this is nothing but the total imbalance contributed by the vertices in the independent set. And this is by definition the total imbalance contributed to the vertices by the vertices in the vertex cover. So therefore, this is the total expression of imbalance which we want to minimize. So this is the objective function. We have already defined the constraints. This is one constraint. In fact, this is two constraints. This is one constraint. This is a non-negativity constraint. So this is the entire formulation of the integer linear program. And we can count that the number of, so there is a message. I have read this from the book, but still didn't understand many things. That's why I asked you to explain. That is fine. So if you have any particular, so I have now explained the formulation of the ILP. If you have any particular question, any particular doubt, then I will be happy to take that. It might be easier if you can unmute yourself and say a few words. Okay, so I'm waiting. You are typing. So when you are typing, let me just complete this argument that, okay, so we have formulated the ILP. Okay, so you're saying, no, I don't have any doubts on the formulation, but if you could take one example on this next session, it would be really helpful. Okay, fine, we can do that. But the thing is, so, okay, so we can take an example, but how many variables are there and how many? So say for every S and every I, we have a variable of this form, and S is itself 2 to the mod X, the choices of X. So if somebody gives you a vertex cover of size 3, so mod X is 3, so you have 2 to the power 3S. Now, number of pockets is K plus 1, that is 4. So you have 4 into 2 to the 3, that is 4 into 8. So you have already 32 variables for a vertex cover of size 3. Okay. And the constraints of this type is 2 to the mod X. So 8 constraints. Okay. And for every pocket, no, so for every variable in the vertex cover, you have 2 such constraints. So you have already 6 constraints. So this is going to be very ugly, even if we take very small examples. So generally, we do not manually solve ILPs. I mean, that would be terribly difficult to explain. But I don't know, we can try. So all these ILP solvers, ILPs, these things, they're implemented programmatically, and because the computer is doing the job, even if there are thousands, millions of variables and constraints, we can expect to get some result within some reasonable time. But it scales up quite quickly. If we do it manually, then neither I will be able to do a good job nor you will be able to understand. That is my feeling. All right. So we have seen that the number of variables and the number of constraints is all bounded by this expression. So therefore, we have a 2 to the this thing and to the 1 ILP solver. And therefore, the imbalance problem parameterized by the size of a given vertex cover of the input graph is fixed parameter tractable. All right. So I'm almost 1 hour 37 minutes down. So we have 23 minutes. So you have some question on the 3 coloring problem. What is the question you have? So you had said last time that you have some doubts on the three coloring question. So you had some questions specifically on the 3 coloring problem. Maybe we can take that question and then we'll move to the questions. Okay. Okay, so as you suggested, let's discuss the problems of the current week assignment. Fine. So you can just write down what is your, so maybe we'll take it later. You can, in your free time, write down in this chat what is your specific question on the 3 coloring problem, then we can discuss it next time. All right, so let's go back. Okay, so is message. Yeah, fine. Yeah, you write down the three coloring question that you have, then we can discuss it next time. So this is the first question of the assignment question, I mean practice questions. So you have been given a graph and a parameter, and you are interested in the coloring question. So you want to color the vertices of this graph using at most three colors, such that uh, for every edge, the endpoints receive different color. So first, let's decide whether the given instance is a yes instance or a no instance.
Yeah, so this is a no instance.
So you're saying that it is not possible to color the vertices of this graph using three colors, such that for every edge, the endpoints receive distinct colors. Let's try this. So you're saying that three colors will not be sufficient. That's what you're saying. Or can you do with three colors only? Is it possible? So these are the colors. This is color one. This is given color two. This is given color three. So is it possible to give color two to this?
Yes, 2 can be given to it because 1 and 2 are
Because
not adjacent.
yes. So if we give two also, then A is only connected to B. And say if this edge was there, then we couldn't have given two. But since this edge is not there, we can give two. So this is in fact a yes instance.
Yes.
Okay. So now, so we have seen a 3 to the power n time 2 to the power n space algorithm discussed in the 13th lecture of this course. And so we have drawn this dynamic programming DP table. So the question is, what is the table entry corresponding to A, B, C, D? So how it is done? So A, B, C, D are what? So A, B, C, D are the vertices of the graph. And for every subset of the vertex set, every subset of A, B, C, D, you have some entry. So what is the space requirement? So how many entries are there if there are n vertices in the graph?
2 raised to the power n entries.
Yes. So it's a order n 2 to the power n space algorithm, as they're saying. And they're computing for every subset of A some value in the DP table. So let me write down the recurrence, otherwise we cannot solve this question. Uh, so this is the dynamic programming recurrence. So they have also mentioned. So we compute and store A of x, which is the chromatic number of Gx. The Gx is the graph induced on X. So X is a subset of the vertex set. So Gx is the graph induced on X. So X is nothing but the chromatic number of Gx. So even if I don't tell you the recurrence, you can tell me what it is.
So its value is 3.
Yes, it's just a it's just the chromatic number. So although I should not solve this question this way, but it is, I'm just saying that it is possible to not compute or not use any recurrence rules and answer this question. But we'll still look at the recurrence relation because that is how it should be done ideally. So it is the minimum over all subsets of Y subsets of X such that Y is an independent set and Y is not phi. And the base, so this is A, X minus Y. And base case is that A of phi is 0. So what it means is that if you consider the empty graph, then the number of colors required to color the empty graph properly is 0. If you color the graph induced on, if you consider the graph induced on a set of vertices X, then one way to do that would be, one way to color the vertices induced by the vertex at X is to compute an independent set Y, which is a subset of X. And because it is an independent set, so all the vertices can be used and given the same color. So since Y is an independent set, there are no edges between the vertices of Y. So they can be given the same color. So one color to color the vertices of Y. And for the rest of the graph, the X minus Y, for the graph induced on X minus Y, whatever is the table entry, we look it up. Does that make sense?
So is there something is there an easy way to show that its time complexity would be of the order of 3 raised to the power n?
Yes, there is. But do you believe the recurrence?
Yes, this seems okay to me. So initially we find the value of, say, if we try to find the value of a1 say, so X comprises of, say, only one element.
Yes.
And
So
then,
in this table, all these entries are one element entry.
yes, so that will be 1 plus, and then one element excluding all the independent set. But then we do not know that how many independent sets are there for a given graph, or that itself is a problem, or uh, rather, because here we need not, I mean, we are not only looking for the maximal independent set add of the thing. So there could be many independent sets, and
Correct. 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 So let's do it for this graph first. So let's try to do it formally. So for the entry corresponding to phi is 0, that is the definition of the base case. So now how do you compute A of A? So how do you, if you replace X by A, so what is A of A? So consider a subset of X, which is an independent set, but which is not empty. Then A itself is an independent set, right? Isn't
yes.
it? So you take A of A minus A, that is phi. So this is phi. So A of phi is 0, so 1 plus 0. So that is the reason it is 1. All right.
Mm-hmm.
So for every singleton set, these values are 1 because we have the similar argument. Now
Right.
consider A comma B. Now you are asking that, okay, A comma is B is there. So A is an independent set, B is also an independent set. So we have to check which one is giving minimum value. So we have two cases. So one case is Y is equal to A. The other case is Y is equal to B. But A of, yeah, go ahead.
Yes, it could even be AB also, AB as well. That could be the third possibility.
No,
That
AB
A
is not an independent set. You have to
here
look
it
at
is
the,
not independent set, but it could have been independent set in the
yes, yes.
in a general case.
Correct, correct, correct. That is true. That
Yeah.
is true. Correct. So that is true. I agree. So
So,
that is how the competition is going on. The question is, how much time will it take? Okay. So the space requirement is order 2 to the n, that is immediate, because there are 2 to the power n subsets of n vertices. Okay. So now So what is the time to evaluate this expression? So let us say that, so let us say x has I vertices at some point. So we are looking at some intermediate x. So the total number of vertices is n. So mod x can go from 0 to n. So we are looking at some I. So mod x is some I. All right. So to evaluate x, so there are two. So how many subsets of x are possible?
So 2 raised to the power I minus 1. I mean, minus 1 would be relevant for us in this case.
All right.
5,
All right. So
5, 5, 5 is of
all
no,
right.
no use. Yeah.
Okay, fine. Yes. But at most 2 to the I.
Yes, yes.
So how many table lookups we are going to do? So there are possibly 2 to the I minus 1 subsets. Maybe all of them are not independent set, but at most there could be 2 to the I minus 1 table lookups we have to do. And then we have to do this addition also. Correct?
Yes. Yes.
All right. So for x having cardinality I, we have to do 2 to the I minus 1 table lookups and 2 to the I minus 1 additions at most. Okay.
Yes.
So now x can vary from. So now first of all, how many I cardinality x's are there? So one cardinality x is how much? For example, here one cardinality x is n, two cardinality x is n choose 2. So I cardinality x is n choose I. Then how many possible x of cardinality I?
NCI.
N choose I. So now for each of these x, you are going to do at most this many table lookups and additions. So the running time is order of summation n choose I. So each of these cases you are going to do, let us say at most 2 to the I operations.
Yes.
Yes. Correct. So I goes from 0 is necessary. 0 is not necessary because 5 anyway we already know. So we are looking at 1 to n only, but 0 to n is also fine. So this is nothing but the binomial expression for this thing. So that is the running time.
Yes. Yes. Yeah. Interesting calculation. Yeah.
Yes. I'm just rechecking if I did everything correctly. So x, there are possibly 2 can choose I options, and for each x, the number of subsets is at most is correct. So this x cardinality can go from 1 to n because cardinality 0 things we have already taken care of in the base case. Yeah, this looks okay to me. All right, fine. So yeah, this is, so if you do it this way, so then you find the all you know. So for ABCD, when x is equal to ABCD, so there are all these subsets are possible. So in all these subsets, first you have to check whether the subset is constituting a independent set or not. If yes, then you look up the value and add 1. So finally you will get this answer if you do it rigorously. And if you are not doing that rigorously, just look at it. I mean, you should avoid doing that, do it rigorously. All right. Fine, let's look at the next question. This is a single question. First of all, we'll decide whether it is yes or no.
So this time we have to check only with two colors.
Yes.
So with two colors, it is clearly no,
Yes.
clearly no.
There is a triangle in this. So triangle is there is a subgraph which is a triangle, and a triangle, because it's an odd cycle, requires three colors. If there is this triangle, this will require three colors. So with two colors, it is not possible. So now we are referring to the same. Okay, so this is the same question, in fact. So there is one missing entry, and but here is a different.
How
There
how
is a
how this
different.
value of ACD is 5? What this 5 indicates here?
So let's look at it. What is the meaning of this table entries? So
Non-empty
let's
independent sets. Okay, 2 raised to the power I minus 1. No, no, no.
number of non-empty independent sets of GS. Oh, so in the previous setting, we were in the coloring setting. So every table entry was corresponding to the chromatic number of the subset. So in this setting, let me just. So in this setting, so every entry is corresponding to the number of non-empty independent sets on the induced graph GS. So there are two things we can do. We can write the recurrence relation, and then we can solve the recurrence and we can do it. Or we can try to do a trick that we can just look it up that how many non-empty independent sets of ABCD are there. There is 3 minutes left. I'll just do the trick today, and maybe I'll just give you 2 minutes to answer the question. You understand the question?
Yes, but but why the value corresponding to A comma B is 2? So does it mean that there are two independent sets having the elements A and B, or what?
So A itself is an independent set, B itself is an independent set, and there are two different non-empty independent sets of the graph AB.
I see. So 1, 2, 3, 4. So 4 will definitely be there. And since ACD is already one of the independent sets, so therefore it could even be ACD would also come. So 4 plus 1, 5. And then the other subset could be uh, so with AV. So uh, I can have AV as one value, AC as one. No, no, no. These have already been taken. AV as 2 has already been taken. So 4 and 4 plus, I don't know. So this will definitely be greater than 5, and therefore, so I'll mark this entry as 6.
So let's count them. So you're right. So A, B, C, D, all singletons are independent sets, non-empty independent sets. So how about A and C?
So the entry for A and C is 3. It shows that together A and C is also forming an independent set. So that, I mean, within this table only, the entry for A and C is 3.
Okay.
And the
So
entry
we,
for A and D, yeah.
so you're saying that this entry is 3. So there are 3 independent subsets for A and yeah. So that's what that is a good observation. So A and D. So for AD, there is the graph induced by A and D. A and D are definitely independent set separately. Now the other
Yes.
possibility is A comma D. So A comma D is also an independent set. That is why AD entry is 3. and AC entry is also 3. So AC is independent set, AT is also an independent set. So you can make this clever observation. So these are the 6 different non-empty independent sets uh, for the entire graph. So the correctness is going to be 6.
But this may result into some more entries. Like say if we consider ABC. So
Okay.
the value of ABC is equal to 4. So it shows that apart from the singletons, ABC itself is an independent set, thereby
No,
resulting
it says that apart from the singletons, there is one more
one more.
non-empty.
Yeah, one more is since the value for AB is 2 singleton, other could be BC and the BC is 2 singleton, or the AC and AC is 3, so therefore AC has already been counted. Yeah, yeah. So this value comes out to be 6. Yeah, right.
Yes, yes, yes. You're right. You're right. Okay. So I think we are at the end of the session. So thanks for joining on a Sunday evening.
Thank you so very much for conducting this session on Sunday.
All right. Also, one more question I want to ask. So we are going to meet next Friday on 6th October, but on 13th October I'm not available. So, but anytime till 11th October I'm available. So 9, 10, 11. So out of Sunday, Monday, Tuesday, and Wednesday, which one is preferable for you?
So yeah, after 6th and then apart from
So between 6 and 11, I want to conduct the session. So 6, we are going to have a session. So between 7 to 11, I want to conduct one more session, which is going to be preponed, and I will not conduct a session on 13th.
okay, so except Tuesday from 6 to 8, any day is fine with me.
Okay, so
Except on Tuesday is on 10th. Yeah.
so you are fine on 11th Wednesday.
Yes, yes, fine. No issues.
So how about Shivang? Are you fine on 11th Wednesday? All right, yes, fine. So I'll communicate to the NPTEL team and then we can decide. So meanwhile, you can ask me that question on tree coloring, which we'll discuss on the next session. All right.
Thank you so very much. Good night.
All right. All right. Good night. Thanks.
Bye.